All right, so last we were talking about the adapter pattern. I will try to finish this off today. So we have a couple of either work days or days that we can do some fun programming stuff, kind of just wrap up everything that we've talked about as a whole. Maybe we also just go into very small bits and pieces of depth of the remaining patterns over the last couple days of class, rather than dive deep into some new patterns without having the ability to use them. But before we get to that, we should finish talking about adapter and facade. So we were talking about the adapter pattern and how it very much seems like a cable adapter or a plug adapter, any adapter that you might, physical adapter you might care to use. Very much like that, where we need to be able to interface with the adapter and the adapter interfaces to another system. So defining the adapter pattern completely, it converts the interface of a class into another interface that the client is going to expect. This allows you to have two classes work together without necessarily understanding how exactly they communicate with each other. They just communicate with a central system. I introduced this last time, but it's like the idea of a language barrier between two people. I speak language number one, the person I'm talking to speaks language number two. We try to communicate, we can't communicate directly, but if we each speak into Google Translate, which is capable of translating into the language the other person speaks, then we could communicate with each other. We just have to have that adapter in between us so that we can communicate back and forth. Benefits the adapter pattern is the client doesn't need to directly communicate to the implemented interface. So the interface can actually completely swap out, and the adapter may be able to pick and choose between the associated targets. So something like Google Translate can translate to an arbitrary language, not just one particular. So it's kind of a multifaceted adapter where you say, take my input and translate it into this output or that output or the other output. And so there's a multi-adapter in there that's capable of interfacing with the target client, because each one of those are separate algorithms that are embedded into the same adapter. So because of this, the way that I ask the query doesn't depend on the target language. I can just speak in English and ask, output what I said in whatever language I want. I don't need to interface with anything about that language whatsoever. You can use the adapter with any subclass of the adaptee. So if you're interfacing with their interface, you can use that with anything inside of that entire inheritance hierarchy. Any of those subclasses, doesn't matter. Here's an example. The client works with the target interface. So basically we have the adaptee at the very end there. So we can work with any of those associated subclasses. But this is the full UML of the adapter pattern. It's not particularly complicated. There's only these few classes, one of which is an interface. Questions about this? We're going to talk about something fun that doesn't arise at all in Java, but arises in other languages. This is the concept of multiple inheritance. So there's one kind of adapter here that we haven't really talked about. We've talked about now an object adapter, but there is a class adapter as well. And this is completely irrelevant, not remotely useful in Java, but as you go through the CS degree and start getting familiarity with more and more languages, you may find some languages where this is useful. So preliminaries, how many classes can a Java class extend? If you're using the keyword extend, just one, right? Can you put a comma in there with another abstract class? The answer is no, you cannot. How many interfaces can a Java class implement? An arbitrary number. Great. But note that this is a Java-specific restriction. Other languages allow you to extend multiple abstract classes. Why in the world would Java care to only allow you to extend one class? Why is that restriction a thing? Any guesses?
So you can't, like, you'd be able to instantiate different, like, abstract classes. Like, you could have, like, 2 different class names that instantiate one object from both.
Kind of, yeah.
What about the image?
The issue arises when we have a multi-level inheritance system. So one example of a language that supports multiple inheritance is C++. And it just gives you the power to do things that, if you look at it from overhead, looks absolutely stupid. And it will just let you do it and let you run into the brick wall that is attempting to engage with it. So Java places this restriction because Java is a very training wheels, hand-holding type of language. It's kind of like the parent that says, you could jump off that cliff, but I don't think you should, so I'm gonna put a wall there so that you just can't do that. Even if you want to, you can't jump off the cliff. C++ says, this is a giant cliff. I'm gonna trust that you're not going to jump off of it, but if you do, I'm not going to stop you. So the multiple inheritance version of this is called the diamond of death. It's a very serious sounding term that represents a very serious concept. So the idea is that we're going to have 4 classes, A, B, C, and D, we're going to call it. And B and C both inherit from A, and D inherits from both B and C. So we end up with a really strange looking inheritance system where we have a class, that class inherits from 2 other classes, and both of these inherit from a single parent class like this. So you can imagine that this class wants to call a method that is defined both here and here. Not a problem, but if both here and here are doing something separate from something that is common from here, then it's going to try to implement what's here, but there's ambiguity about which implementation to use, which creates undefined behavior. C++'s compiler is not capable of distinguishing between one and the other, so what you get is kind of at the compiler's whim. And it may end up doing something that's completely unknown to you, and it's a nearly impossible bug to fix, catch, or deal anything with. You can do some really seriously bad things if this is implemented. It's just terrible. So B and C override a method from A. D does not override it. So D tries to implement it. Does it use the implementation from B or the implementation from C? We don't know. So Java just says, you're never going to run into this because you can't extend from multiple abstract classes. If you want to emulate that behavior, then they need to be interfaces and you need to implement from multiple interfaces. But you can't have logic in those interfaces, so you can't create the diamond of death with interfaces. You have to have abstract classes where there are implementations in abstract classes for which you extend from both of those. So this is kind of outside the scope of this class, but I just wanted to show that there is an additional kind of adapter design pattern that is only relevant in languages that support multiple inheritance.
Will this be on the exam?
No. No, I care much more about the actual adapter pattern applied to the language that you've been coding in. But this is just kind of general knowledge of if you have a language that supports multiple inheritance, one, be super careful. It's really easy to jump off a cliff in programming where there are very few implications for this. But as soon as you're in a system that is connected to a network, and maybe you're producing a diamond of death by sending things through the network, you can end up overwhelming and crashing your network in a way that it can't recover from. So you create multiple days worth of downtime while IT figures out what in the world happened from this relatively innocent diamond of death that you accidentally implemented.
So does the adapter just take stuff from both those classes and then you have one class to extend?
Yeah. Yeah, that would be the idea. Has anyone tried plugging something like an Ethernet back into the same device that it came from?
Probably by accident.
I might want to.
Did anyone know what happens if you have the same device? You take an Ethernet cord and it has two Ethernet ports in one side, in the other side.
Or does it see its own MAC address?
It basically sends requests to itself, but those requests can't be resolved. So it creates process after process after process after process after process. And then eventually your network just doesn't respond to anything because the network is fielding all of these requests from the same system that it can't resolve. So it ends up crashing the network. Or hanging at the complete largest amount of memory that it could possibly use. So no system can interface with it because it's getting so many requests so quickly. So yeah, only do that if you really hate the person or really hate the company you work for and there are no cameras. I did not tell you to do that. It didn't come from me. So in languages that do support multiple inheritance, we get class adapters being possible. So we're able to do something like this. This UML is not possible in Java, but it is possible in languages that support multiple inheritance. So this is where the adapter would be placed, and your adapter could extend both the target and the adaptee to be able to work with both of them at the same time in the same code without having to use composition at all. So let's see an actual real world example of an adapter and how that actually comes to be and what use it can be. Back before collections were actually called collections, they implemented an enumeration interface instead of the modern collections interface. So the old collections, vector, stack, and hash table, all of which have been deprecated. If you notice, there are some really legacy things if you use the actual built-in Java stack. It's actually a really ugly data structure, and you can implement it better yourself than the way that the actual stack is implemented. They had a method in that interface called elements that returned an object that you could use. It's very similar to our iterator. Our collections have an iterator method that can be used to iterate through a collection. But very old applications can still use the enumeration interface. It still exists. But the difference between the enumeration interface and the more modern iterator interface is that an iterator can remove from a collection while you are iterating it. Have we seen this happen? You have a has next, a next, and then you can actually remove. Have you gone through the logic, those of you who have taken or are taking data structures, about how that actually works? If you're removing something in the middle of iterating through it?
Yeah, just like passing over to the next.
Yeah, so basically, like you have an array of 4 elements, and as you get an iterator, you do the iterators next to look at this element, and then you want to remove this element, which is going to push this element here and this element here. You don't actually want to advance after you do that, so you need some additional logic that says, if we were going to advance and you remove, don't advance, because the next element is actually in the same position that you just looked at. So enumeration doesn't support that at all. Enumeration straight up says, I don't know how to remove things. So if you want to do that, you can't. So we use iterators. We can remove elements as we step through them. Great. Now you need to interface with a code that still uses the enumeration interface. Maybe there's some really legacy system. Maybe it's some governmental system. Maybe it's, going to the DOL and getting your license. I'll pitch for FAST here. You don't have to do that anymore because FAST has revolutionized that. I wasn't paid for that. That's free advertising for you, FAST. Feel free to send me money. So we implement our side using iterators because we want the ability to be able to remove if we're interfacing with anything other than this really legacy system that uses an enumeration. We could also use an enumeration, but anytime we used our code, we would never be able to remove from it. That's not ideal. If we interface with some other system over here that actually uses an iterator, if we use an iterator, then we can remove things. Great. But we still want to be able to interface with this one legacy system that uses an enumeration. So we want an adapter that's going to sit between the enumeration interface and the iterator interface that's going to allow us to communicate back and forth with this legacy system. So here are the target interfaces. We have the iterator that has the has next, next, and remove that we've come to expect. We have the enumeration that has methods has more elements and next element. You can see we've come a long way in our language of API development. So go ahead and in groups, attempt to design what you can with this adapter. Find one or two people next to you and see if you can come up with the logic where we're implementing our code using the iterator interface. We want to be able to communicate with an enumeration interface. What class sits in between these where we can make a request with an iterator? It's going to convert it into a request for the enumeration, field the response from the enumeration, translate that back to iterator speak, and do the thing for the iterator. Take a stab at it. See if you can come up with that logic.
That was a good idea.
So remember from before, the first question you should ask yourself is what interface does the adapter implement? Does it implement the iterator interface or does it implement the enumeration interface? Once you figure that out, then we need to start passing in. We need to be able to support everything from the interface that it implements. It's going to have some object in it that it gets populated from the constructor, and then it needs to be able to do everything from the interface that it implements by translating from what the object that is its field can do to what the target interface, what methods they support.
So if it's next, it's information on so this is inherited. Yeah.
So instructor.
I was thinking of that inheritance.
5%.
Yeah, I forgot to charge that last time.
That's nice.
Yeah. do one of them, please. Has next is just a numerator. That has components.
So I've heard talk about how we could handle the iterators has next and next because they map directly to the enumerations, has more elements and next element. What about remove? How is that gonna work?
Next.
Yeah.
Or down the bar.
That's a link list, but
Now, the issue with that then is that it's not actually gone. So you would need to either figure out all of the logic for that, or if you really don't want to do that, you can just have an unsupported operation. Because the enumeration can't do that. Remember, the iterator can do that. It has a remove, but we need some way to emulate that within an enumeration. These are the only tools an enumeration has. So an enumeration straight up can't remove. We cannot ask the legacy system that supports enumeration to do that. So we're going to end up making a custom exception and throwing that exception if someone attempts to use the iterator to remove when it's communicating with an enumeration.
Have a word.
was possible.
Yeah. Just can't.
Where? I think there's like a phrase of Dutch or something. That was done.
So the enumeration iterator is going to have the same three methods that the iterator does. But has next will call has more elements, next will call next element, and remove will break elegantly. So we can't always convert one interface into another. We've seen this immediately right now. So here's what the code would look like. We have an enumeration iterator. The correct answer for what it should implement is iterator, because we want to be able to support anything that an iterator can do. That means to construct it, we're going to pass an enumeration object. That's going to be set as the field. Then we want to be able to support everything that the iterator can support. So we need to have a has next, and a remove in order to be able to, I'm doing something up there. To be able to support the iterator interface that it's implementing. You can see that there's a direct association between has next and has more elements. A direct association between next element. And then with remove, we just give up. We throw a new kind of exception that you probably haven't seen before, an unsupported operation exception. This exists within Java. You can throw this at any point, but it basically says that we can't support what you have tried to do. We need remove there in order to be able to implement the iterator interface. If we don't have it there, we can't. This won't be legal code. So we include remove. It's just that if anybody calls remove, we throw an exception. Note that throwing this exception doesn't necessarily crash the program by itself. If it's unhandled, then it will. But you could, in any client code that uses this adapter, surround that in a try catch, say, try this enumeration iterator dot remove, and then catch the unsupported operation. And then do something with that. So it's always better to throw an exception than it is to straight up crash the program. And that's so that the client can choose to recover from that if they so choose. They just show the logic of how they want to recover from that exception. And then you're basically putting the burden on them that says, I can't handle what you just asked me to do, but you can come up with the logic for how you want to proceed if you want to. So exceptions are always the way to go. Questions on this adapter? How this adapter would work? It allows you, the person with an iterator, to make one of these objects. You just have to instantiate an enumeration object, pass it in, and now you can, or you take the enumeration object that you get back from a legacy system, pass that into this adapter, and start making calls to it. Using the iterator's language. This is an enumeration that has been disguised as an iterator, and the only reason we would know that it's disguised as an iterator is if we try to call remove. Then it would reveal itself and say, I actually can't do that, sorry. Think of it as a spy in some country that doesn't speak the local language. Looks like a member of that society, but as soon as you walk up to it and ask them a question in that language, they just look at you like, I'm actually a spy, please don't tell anyone.
I know beer food is bad.
Yeah, there we go.
And the adapter for the remove just like do nothing.
Because then it looks from the client's perspective like it was successful. That's a good question. Remove could do nothing. You could choose to do nothing, but the client code would return and it's like, you've been successful. You have removed this element and the element has not been removed. So you're kind of lying to your client. I did it and you didn't actually.
You wanna hear a fun story?
Yeah, sure.
My friend showed me this game he coded. I thought, oh, this is pretty cool. You have a little ping thing in the top right.
Yeah.
And I go, oh, that's just a random number generator. And it shows your ping. Yeah.
Yeah. The next best thing is a random number generator that just straight up returns a single value. Return 4. The best random number generator.
Yeah, it could be.
Yeah.
Maybe he's just getting 4 of it.
Yeah, who knows? You have to look at the implementation. It's like oh man, graduate students found a product called is even, and the free tier will answer is even for any integer between like 1 and 1,000. If you want between 1 and 100,000, you have to pay a certain membership. If you want between 1 and a larger number, it's a tiered pricing system. Which is really funny because you can take any result of is even of a lower value and convert it into a larger value yourself. So it's just funny, but. So there's one more thing that we might care to do surrounding this idea. And instead of communicating between interfaces, what if we want to take a large interface and we want to make this large interface a smaller interface? So we don't necessarily need to do a big adaptation process, but it's a very similar idea to be able to take, here's a complex interface. I'm going to write a simple interface that does all of the work of the complex interface by calling that complex interface in some order. So you can actually go through the process of simplifying it. So the example the book uses, and I'm going with this because it creates fun, engaging examples. You're older than you actually are, and you're designing a kick-ass home theater system from the 90s.
One of my dreams is still to have a sweet home theater.
You and I get along. We understand each other. The rest of you, imagine like you're one of us. So here's the complicated system. There's an amplifier, a tuner, a DVD player. What is that anymore? A CD player. Oh my gosh, dating ourselves. There's a screen, a popcorn popper, because what's a home entertainment system that doesn't make popcorn for you? Theater lights, so you can dim them ahead of the movie, and a projector for projecting it, because we only have 20-inch screens. We're in the 90s. So you need to project it onto a wall or something. So here is the complicated interface and all of its inner workings. So if we want to sit down and watch a movie in our home theater system, we need to follow a sequence of steps. We need to turn on the popcorn popper, start the popper popping, dim the lights, put the projector screen down, turn the projector on, set the projector's input to DVD, put the projector on widescreen mode. Oh, man. Turn the sound amplifier on, set the amplifier to DVD input, set the amplifier to surround sound, set the amplifier volume to medium, turn the DVD player on, and start the DVD player playing. So a lot of steps of engaging with this system. You can imagine writing code for doing this. The process for doing this involves communication with 6 different classes to do this. Yikes. Lots of steps before we actually get involved with actually watching the movie. Kind of a problem. Think about the movie finishes and you just want to kick everybody out and go to bed. But no, you need to actually go through this same 15-step process in reverse to turn everything off. It's just as complex if you wanted to just sit down and listen to music. Man, how times have changed. Then in the future, you want to upgrade your system. Oh no, we have to completely revamp this procedure and edit all of the associated code to go through the new procedure to interface with the new objects. So this is the introduction for the concept of the facade design pattern that is going to be able to extract this complexity and create a single call that's going to do all of these things at once and assign it an associated label. So you can imagine doing all of these steps all at once and assigning it the start movie button or the start movie example where we go through and do that. So the client code now, instead of instantiating and calling methods for all of these objects, is only going to instantiate a single facade object that now goes through and does everything. When it receives a command, it knows, kind of like a preset, it knows what is meant by start watching a movie, and it will call the 15 steps for you, so you don't have to worry about it. So it would look something like this. Time to zoom in. Let me figure out where my mouse is. It must be on the other screen. So we have a single facade that has commands that you could throw at it, like watch movie, end movie, listen to CD. And the facade knows exactly how to interface with the complicated interface so that you only have to work with the facade interface. We're just abstracting all of these calls and ideas into names that we can give them. So now here's what this code might look like inside of the facade. So we have a home theater facade class that is going to have all of the associated fields, a constructor that takes in all of these parameters. Hint, hint, we might want to use a design pattern to shorten this crazy long list of parameters to this. We set all of this, and now we're ready to call the actual methods that are capable of interfacing with the facade. So now we make a watch movie method that goes through this process of calling all 15 of these commands, and we have a single name for it now, watch movie. So if you call the facades watch movie, it interfaces with the complex home theater system and delegates all of the work. The same for end movie. It goes through all of the steps to end the movie and turn your system off, rather than having to think about each individual task. So it's pretty straightforward. It's just another form of abstraction, and really all design patterns are some form of abstraction, where you take a complex system and you simplify it in some regard, or at least you simplify the interaction with it. Even if the underlying representation has gotten more complicated, you have simplified the interaction with your system. So we can actually use the facade. And now we see how simple the client's code is. Inside of main, we just make the associated components that we need. We make a home theater facade, we pass it all of the objects that we just made, and then we can just call the home theater dot watch movie. And suddenly it plays the movie. Great, everything's handled for you, there's no setup. When you're done, you call end movie, and then it does all of the associated things. So with just these couple calls from the driver class, you can do all of the things in the output over here. Way more calls than you actually made because you set up the facade. So this takes a complicated system or a complicated sequence of commands and turns them into a simpler set of commands for interaction. This is very useful if you are designing a very complicated system and want to make the interaction with that system as simple as possible. That's when you're going to want to use a facade. As a computer scientist, you should know that whomever is using your code is the least intelligent person you've ever met. They're going to find a way to break your code. They're going to find a way to complain that it's not easy enough to use. So you need to write your code like a baby is going to be using it and guide your user through it. Any ways that you can simplify it will greatly come back to benefit your system. It will get better reviews. It's so simple to use. It does so many things. Those kinds of reviews come from using the facade pattern. So a formal definition for it, unified interface to a set of interfaces in a subsystem. We end up with a higher level interface that interacts with a lower level subsystem to make that subsystem easier to use. So you take a complex subsystem, you write a facade for that subsystem, and now the client no longer has to engage with the subsystem at all. They just engage with the facade that engages with the subsystem. Questions on what facade is or how it is used? I feel like it's probably one of the more straightforward patterns, but I'll happily field any questions.
I mean, you could just say the facade almost acts like a director in a lot of cases.
Yeah,
Just-
it's gonna interface with something complicated that the client doesn't need to know about. So it's similar to a builder's director class.
Yeah.
For that reason, it's similar to command where we assigned commands or like undo as a single button to know what was the last thing that was undone. We just specify now instead of a field of the last thing that was done, we would now have an actual set of methods that define the behavior that is done. So there are similarities between the design patterns. And again, if we go all the way back to the beginning of the class, when I said that design patterns are kind of a hodgepodge of ideas that come together, there's not really a formal definition of design patterns and a universally accepted set of them necessarily. This is just what has come to be. You can start to see the similarities between different patterns because it doesn't come from a formal background. It comes from just a bunch of people who had ideas, which I think becomes apparent as you look at them deeper and deeper. You realize that there's not as much difference between them as you might think, or the relevance for them. Sometimes you could choose this pattern or this pattern, and either one of them will work with slightly different pros and cons. Takes us to a last OO principle for the course, the principle of least knowledge. This says that you only want to communicate with your immediate friends. If you have friends of friends, talk to them through your friends. Don't go try to approach them directly. Keep your friend group small and close to you. When you design a system, for any object that's in that system, you want to think about the number of objects that it's going to be interacting with. You don't want it to have a wide social network. That becomes a huge maintenance nightmare. You can think of, imagine having 100 close friends. Even if there was a 5% chance that a given friend reached out to you on a given day, that's 5 conversations you have to handle every single day, on average, just from your friend group. That is overwhelming. Too many friends. So in the OO example of this, you just want to make sure that everything is connected just to its few closest neighbors. And they're not reaching far in a way that could be routed through the existing implementations of its closest friends. When you have this many dependencies between that many classes, so you have one class that's talking to 100 classes around it, then any one thing changes and your system just stops working. Because there's a lot of coupling going on there. There's not a lot of extendability. It's a fragile system. One small tweak, the entire system breaks. Which means that anytime something changes, it's going to involve a lot of work in order to maintain that system. It also means that in the real world, you're going to be joining a company where a project is already underway. You're not starting at the very beginning of the project. You have to interface with code that somebody else wrote and get to the point where you can start contributing to that project. It may be that you're assigned something, but your boss knows that you're really good at something else. So in the middle of implementing something, she says something like, take your existing project, give that to Dave over there, and start work on this project that I know you're going to be good at. And if your code doesn't adhere to the principle of least knowledge, Dave's going to look at your code and just faint or quit on the spot. Nope, I'm not dealing with that. So the general principle is if you have an object, you only want to call methods that are part of the object itself, part of parameters that are passed into that object, or an object that that method has created or instantiated directly itself. If you're calling something outside of the scope of that, it's not a close friend to this object. Figure out some system that one of your close friends has for doing that. You don't want to create all of these dependencies with other subsystems, other objects within your subsystem. You can also, of course, invoke methods of components of the object. So if you have an aggregation or a composition where one of your fields is another object, of course, you can call its methods. We have time for this. Maybe we do. So here's a car class. We want to see what are its close friends. Well, a car has an engine, so the car should be able to communicate with any methods of the engine. It has doors. So when we start, it makes doors. So because it makes doors, we're creating an object. So any methods that exist within the doors class, you should be able to access. We passed in a key as a parameter into the start function, so we can call anything from key. Same thing for, I guess the dashboard display doesn't really do anything here, but you get the idea that when we have access to objects of type key and doors and engine, those are the only methods we should be calling associated with those objects, not something wildly different from that. And in the home theater example, you can see that all of its friends initially are all of the elements of the subsystem. So what the facade allows you to do is make, instead of the client having to deal with a bunch of different subsystems, it has to do with just a single object that also communicates with all of those subsystems. So that helps to adhere to that principle. All right, I think that's basically everything I have for you with regards to adapter and facade. Let me know if you have any questions about it, but we'll probably cover one more thing in a bit of detail tomorrow. But beyond that, I don't have too much of a plan for Thursday or Friday, so we can either have a work day or a Project Euler or Caddis day, something of the sort as we wind down, get a chance for you to work on your observer lab that we posted today. And you can also expect a study guide by the end of the week, because you are one of the last finals. And we'll have a study period next Monday where you can ask me any questions about that study guide. See you tomorrow.
Have a good one. This is room
For the final?
for, again. Today?
Oh, for Harley?
Yeah.
I think he's planning to come here.
Okay.
He was a little bit late last time, and then by the time he arrived, there was nobody here. That is good. If you want to talk to Harley about anything related to your projects, he'll be here eventually.
Maybe would have seen it if you did.
Yeah, I think the plan is to get through another lab today.
I'm just gonna show them all mine. Okay, so no, this works.